You know, in any RF system, there's this one connection that can totally make or break your performance. I'm talking about that link between the transmitter and the antenna. Getting this right, it's everything. So today, we're going to break down exactly why it's so critical. Let's dive in. All right, just so you know where we are, this is part 10 of our deep dive into radio frequency propagation. We're pulling all this from a really detailed report by the RFI detectives over at Virtualization Options LLC. And hey, if you're an RF tech or engineer, you already know this stuff is the bedrock of what we do. Okay, let's kick things off. Section 1, the vital link, from source to space. We're going to start by tracing the physical journey of our signal. From the circuit where it's born, down the line that carries it, and finally to the antenna that launches it out into the world. So, take a look at this. It really nails a key concept here. An antenna is so much more than just a radiator. The best way to think about it is as a transitional device. Its whole job is to take that guided wave traveling down the line and efficiently convert it into a free space wave that can, travel through the air. And that transition point is absolutely critical. And that pathway we're talking about? Well, that's your transmission line. It's basically the conduit for all that electromagnetic energy. Doesn't matter if it's a coax cable or a waveguide, its one and only job is to get that energy from point A to point B with as little disruption, as little loss as possible. But, here's where things can get a little tricky. That handoff of energy from the line to the antenna, it isn't always smooth. I love this analogy. It's like a really bad handshake, where the energy gets kind of fumbled and not everything is transferred properly. And that right there is the core problem we call impedance mismatch. So, what governs this handshake? It's a property called impedance. At its heart, it's just the total opposition a circuit presents to an alternating current, and it's made up of two parts. You've got resistance, think of that like simple friction, and then reactance, which is a bit more complex. It stores and releases energy. The key, for that perfect handshake, the impedance of the source and the load have to match perfectly. Okay, so this brings us to the million-dollar question for any RF tech out there. What actually happens when those impedances don't line up? Well, the immediate effect is something called reflection. As soon as that signal hits the impedance boundary, a chunk of its power just doesn't make it into the antenna. Instead, it bounces off and gets reflected right back down the transmission line, heading straight for the source. It's literally an echo inside your RF system. And this is what happens next. That reflected wave starts traveling back down the line, and what does it do? It interferes with the original forward wave that's still coming. So where their peaks align, boom, the voltage goes up. Where a peak meets a valley, they cancel each other out. This whole interaction creates this stationary pattern of high and low voltage all along the line. And that, my friends, is what we call a standing wave. Now, the really crucial point here is that this isn't just some abstract, theoretical problem. A mismatch leads to very real consequences. We're talking power loss, an antenna that just isn't radiating efficiently, and in high-power systems, that reflected energy can come back and literally fry your transmitter. It's a total recipe for disaster. All right, section 3, the goal, achieving maximum power. So we've laid out the problem, right? Now let's flip this around and talk about the solution. What's the fundamental goal for any RF system? It's actually pretty simple. The goal is what we call maximum power transfer. We want to make sure that every single watt we generate at the source actually makes it out of the antenna and into free space. Efficiency, that is the name of the game. And the way we do this, the engineering practice for it, is called impedance matching. It's a deliberate design process. What we're doing is making the load impedance, in this case, our antenna, look exactly like the source and transmission line impedance. When they match, poof, the reflections disappear. And man, the difference is like night and day. In a matched system, you've got minimal reflection, maximum power transfer, and the whole system is just humming along, super efficient. But in a mismatched system, you get the exact opposite. Reflections everywhere, power loss, and just plain old inefficiency. So moving on to section 4, the metric, quantifying the match with VSWR. Okay, so we know the goal is a perfect match, but how do we actually measure it? How do we put a number on the quality of that handshake we talked about? Well, that's where a fantastic little metric called VSWR comes into play. VSWR. It stands for voltage standing wave ratio, and it is the key metric here. It's just a simple number, a ratio, that tells you exactly how efficiently power is getting from your source to your load. Think of it like a report card grade for your impedance match. So let's just quickly run through how this all happens again. First, you get an impedance mismatch at the antenna. Step 2, that mismatch causes part of the signal to reflect back. Step 3, the forward and reflected waves start to interfere with each other. And finally, that interference creates the standing wave pattern. With those telltale voltage peaks, we call them Vmax, and voltage valleys, or Vmin. And that brings us right to the heart of the definition. The source material puts it perfectly. VSWR is simply the ratio of that maximum voltage to the minimum voltage you find along that transmission line. And the math behind it? It's beautifully simple, really. You just take the maximum voltage, Vmax, and you divide it by the minimum voltage, Vmin. That's it. That ratio is your VSWR. So it makes sense, right? A bigger difference between the peak and the valley means a bigger ratio and a worse match. Now, this table gives you a really practical feel for what these numbers actually mean out in the field. Look, a perfect 1-to-1 match, that means 0% reflected power. All your energy is getting out. A pretty good match, say 1.5-to-1, you're only losing about 4%. But check this out. Once you hit 2-to-1, you're already throwing over 10% of your power right back at your transmitter. And that can seriously degrade performance. Okay, so let's boil this all down to the key takeaways. Number 1, we are always aiming for a low VSWR. Number 2, 1-to-1 is the holy grail, the ideal, perfect match. 3, a high VSWR is a big red flag for inefficiency and reflected power. And that's why, number 4, measuring VSWR is absolutely fundamental if you're trying to diagnose and optimize any RF system. So this all leaves us with one final, very practical question. A perfect 1-to-1 match is the ideal, sure, but real-world engineering is all about trade-offs, isn't it? So I want you to think about the systems you work on. What's an acceptable VSWR for you? How much performance are you really willing to trade for practicality? That's a question every single RF pro has to answer for themselves.